Hello everyone and welcome to the SoilWorks webinar. My name's Adam Kane. I'm going to be taking you through proceedings today. So what I'm going to quickly do now is do a quick sound check and also ask you if you wouldn't mind raising your hand if you can hear me and also see my screen. If you wouldn't mind passing a comment in the comments box, it would be very much appreciated. I'll start in about 30 seconds. I see we've got a really good turnout and everybody that registered is turned up to the webinar today, so I'll make a start. So first of all, this is about SoilWorks and we'll be focused on slope stability analysis for embankments and reinforced slopes. My name's Adam Kane. I'm the technical support engineer for Midas in the UK, based in London. You'll see our telephone number and our email address on the screen, so if you are having problems, please contact us. Okay, so we'll just go through some of the housekeeping rules and how to use the GoToWebinar for the next couple of slides. If you can't hear me, then your computer might be set to mute. If you'd like to set your screen to maximize it, just by clicking the two little boxes in the top right hand corner. If your screen happens to go blank during the webinar, it's more than likely you've got your screensaver set to on. So if you wouldn't mind either wiggling your mouse throughout or just turning off now. So here is the GoToWebinar dialog box. I'm sure you've all seen this before, but if you would like to shrink it down, just press the red arrow key. If you have any questions, place them in the chat box. We do have a technical support engineer on standby to answer questions as they come in, because we are limited to our half-hour slot. If your question isn't answered during the webinar or in the short period at the end, then we will be sending out email correspondence after. So we're just going to go through the webinar contents. First of all, I'll give you an introduction. Then we'll go through the numerical approaches, the reinforcement for slope stability, the finite element analysis, limit equilibrium analysis, and also the report at the end. So first of all, we're going to focus on the slope stability and for embankments and cut slopes. A slope is stable under its own self-weight, which is why we call it a geostatic slope. So that means it's just its self-weight that it's acting under. Instability in slope occurs when external forces occur in it's such as rainfall, groundwater or surcharge on the loads and things like that. Failures in slope occurs when the shear stress generated due to the self-weight and external force exceeds the shear strength of the ground material, i.e. if anything's added to the slope, then it will cause it to fail. In any slope stability analysis, the important task is to account for progressive failure surface. The failure starts as an initial deformation, which then propagates throughout the whole slope, causing the ultimate failure. So just moving on to the next slide. So here's our graphics for this. So as you see in stage 1 there, the slope is under geostatic condition, under its own self-weight, so it's completely stable. In stage 2, the instability causes by external forces acting on the slope. As you can see, we've got the FEXT, or the external forces acting on it. And then stage 3, the failure occurs when the induced shear stress, T, exceeds the shear strength of the material. So as you can see, you've got T and W. So here are some pictures of some failed slopes. As you see here, obviously the one at the bottom has been created by a large amount of rainfall, and the slope has failed because of all the poor water pressure has filled the voids. And you've also got two other failure points at the top there, just some examples for you. So now we're going to focus on the numerical approaches for slope stability analysis. So we've got two analysis approaches are considered. You've got the limit equilibrium method and the finite element method. So first of all, we'll just focus on the LEM and the analysis principles. So divide the slope into vertical slices and calculate the safety by considering the equilibrium of forces and the moments. For the finite element method, on this line it's the required finite element modelling. Ground material is represented through constitutive models. Material behavior is non-linear in the form of the plastic and elastic method, or the elastoplastic theory. So for the analysis results, you get the results for the factor of safety and the critical failure surface. In the finite element method, you get the results for deformed shape of the slope, the stress distribution, and the factor of safety. For the input data, you get the input cohesion and friction angle for soil layers in the limit equilibrium method, or LEM, which I'll constantly refer to during the webinar. The FEM method is the input cohesion, the friction angle, and the elastic modulus, the Poisson's ratio, dilatancy, etc. for non-linear analysis. So now just to focus on some of the pros and cons. So for some of the pros, the LEM is more of an analytical approach for slope stability, and many practical cases is this where LEM has been used for slope stability analysis. In the FEM method, you can analyse different ground properties, for example effects of delineation on shear failure, and you can get the results for displacements and stresses as well. So the cons, or the disadvantage of the LEM, is there's no output for displacement and stress in the soil. Importantly, before performing analysis, the failure surface has to be assumed, and for the FEM, the stability evaluation could be hard to interpret and requires experience of the engineer. So now we'll look at the reinforcement for the slope stability. So just start off with anchors, which increases resistance of the resistance of the slope against sliding. Anchors can be pre-stressed as well, where you can have the pre-stressing and part anchorage resistance to the movement of the soil mass. Nails, which are the most commonly used reinforcement. Nails are easy to implement as they require no pre-stressing, but that has to be compensated by larger cross-sectional areas, and based on the cross-section, the resistance could be axial or in shear direction. So now just briefly talk about the strip and fabric, which is made out of a steel structural material and is resistant from pull-out stresses or strength. It has a pull-out strength. Geogrids. Geogrids are reinforcements resist loads in the axial direction only. Only tension is resisted and there's no compression is supported. Hence they can be represented as truss elements in finite element analysis. And just finally, piles. Piles can be used as reinforcements for slope stability. The main resistance against sliding comes from the shear friction along the pile shaft. Excuse me. So just moving on to the finite element method, or FEM. So finite element is a precise method for analysing slope stability, as we don't need to make assumptions for failure surfaces. In finite element for model domain, force equilibrium, node and compatibility conditions, constitutive equations for ground material and boundary conditions along model edges are satisfied. Simulates the actual failure mechanism and automatically determines factors of safety and failure behaviour in the slope based on non-linear analysis. In situ conditions based on poor water pressure profiles and other things such as that nature can be best reflected in finite element analysis modelling. There are two types of FEM models. The first one is the strength reduction method, or C-Phi method, and the second one is the stress analysis method, which is a hybrid of the limit equilibrium method and C-Phi method. Finite element analysis is an iterative process where for each iteration force and displacement compatibility is satisfied for each node. This increases the analysis runtime in finite element method analysis. The strength reduction method was proposed by Zankiewicz in 1975. The shear strength parameters, cohesion and internal friction angle of ground materials are gradually factored down till divergence occurs in the model. This is when the slope is said to be failed. Critical cohesion is given as C critical, which is C initial divided by the factor of safety, and critical friction angle is given as phi. Critical tan inverse of tan, initial friction angle divided by the factor of safety, as shown in the expressions here on the screen. It is important that to accurately obtain the critical factor of safety, the increment should be made in small steps. Typically, initial factors of safety is kept as 1 from Jangball's method, and then it is incrementally increased, which, checking the results for ground deformations, the user should keep the value chosen for delineacy and the delineacy angle in his mind. When the delineacy angle is equal to internal friction, the internal friction angle, the yield surface and plastic potential surfaces are equal, making the stiffness matrix as symmetric. This would cause faster convergence in analysis, but it might give unrealistic deformations. So when the delineacy is lower than the friction angle, the computation time increases slightly, but the deformations are more credible. So the figure at the bottom illustrates the process of obtaining the critical factor of safety. The stress field computed as a gauge point A, is represented as a mole circle. The initial failure line is shown above the mole circle, where the strength parameters are incrementally reduced till the failure line becomes the tangent to the mole circle. At this point, the material has failed. A collection of such points could cause a global slope failure if there's multiple points on a slope. So now we're just going to move into the modelling space. I'm just going to bring over SoilWorks now. As you can see, this is the user interface. And what we're going to do is just bring in a CAD file and the geometry, so just the soil nail reinforced bank. As you see, I've got all the materials and everything predefined, and also the structural properties. If you want to create your own, you can just go into ground materials and you can select them all and manipulate all the properties. You can also create your own database. So as you can see, I've got a multitude of different databases that have been created. So now I just want to define the nails themselves and make them into elements. So I'll just select all of those, and we just use the neat drag and drop feature straight from the works tree, and those have been created. And I just use the type in SS, which is the smart surface feature, which we've just used our CAD command line at the bottom there. You can also find it in the ribbon technology. So now I just want to create the strata, or the different material types, by dragging and dropping them from the works tree. So just take all the weathered rock, and let's do the top layer, which is the weathered soil, and we can also look at the properties for these as well. So here are the properties. So now I'm going to mesh these just using the smart mesh feature from the ribbon technology, which is a very fast thing to use. So just generate all the elements, and as you see, that's our mesh being created. So I'm just going to delete the mesh set for the structural nails. We can create mesh sets for structural elements using the existing ground mesh. So I'm just going to do that quickly now by creating an element. So I just got to select all of them. You just select the nodal point, so using the snap feature, select to the start and the finish, then just entering it and just quickly do all 5 of these. So the modelling is very easy within the working space. Okay, that's all been created. I can check those in the actual window and also rename them. So I just want to rename them nails. So now I'm going to put the water level, so we can just quickly do that. We just select it. So we just define the water level. So just select the planes or the surfaces we're going to apply them to. Just click OK. I just want to do the ground support conditions automatically, which is another neat feature within the program. So supports, and as you see, it's just given the supports all the way around. And we can check the supports in the works window. So now we look at the analysis case and create the SRM analysis case. So we just add all the meshes, all the boundary conditions, and all the load sets. And the check on the analysis control data, and then the initial water level, and we just put a water level, so, which is what we've actually got on the screen. Then we just get a close, and that's that load set created. So now going back into the presentation, I'm going to talk about go on to the next slide. We talk about the limit equilibrium method, or the LEM. So this is an easy way to use, easy to use method where presumptions about a failure surface has to be made by the engineer, so it's down to the engineer's judgment. Location of the probable failure surface depends on the engineering judgment. Usually a system of grid or arcs are created to find out critical failure surfaces. Ideally, the critical grid point representing the minimum factor of safety should lie at the centre of the grid, which I'll show you an example of in a moment. SoilWorks can simplify this tedious task by automatically defining the failure surface. The various types of failure surfaces and situations can be considered for the LEM analysis. And the arch failure surface, the arches are drawn based on tangents to grid points or passing through a critical point. The polygonal or multilinear surface and the tension cracks particularly are partially or fully saturated, so i.e. the actual tension crack created in the surface of the slope when water seeps into it. The failure surface should emerge out of the model at both ends, and you see from the second diagram no 2 points on the failure surface should lie on a vertical line, and the failure surface cannot go beyond the model geometry. So now we talk about the LEM analysis methods. So one could perform limit equilibrium analysis based on different methods, as you can see here. Analysis methods are listed in the following tables on the left, in the form of the Frobenius, the Bishop and the Jabul, which are commonly used and also recommended by the EC7 or Eurocode 7. Solving interslice forces in an indeterminate problem, or is an indeterminate problem, hence several assumptions have to be made, and the table shows various assumptions made by each analysis method to solve the unknown forces acting on the splice. So just go down through all of them. The Frobenius, so there's no interslice forces, and under the vertical equilibrium there's no, horizontal equilibrium is no, and also the moment equilibrium is yes. So just going on the Bishop, so I'm sure you can read these, so I'll just flick straight through them, and then there's horizontal, and then it's yes, no, and also yes. We're just going to skip straight through this, I'm sure you've looked at them. So now we're going to go through the LEM analysis methods in more detail. So just to go from the top down and just say, this table outlines the strengths and weaknesses of different analysis methods. So I'm just going to read the Bishop, Jabul and Spencer. So just some of the strengths of the Bishop is the short analysis time, applicable to the arch and polygonal methods, of carrying out, and the weaknesses are the inaccurate results when horizontal force is acting, such as for seismic analysis. The jambu, which is, as its strength is a short analysis time, and is also suitable for shallow slopes. And the weaknesses is more conservative results. For the Spencer is the applicable to the arch and polygonal analysis methods, and it has more accurate and safety factors involved, but the weaknesses is the long analysis time and the more sensitive convergence. So I'm just going to go straight through to the next slide. So before we talk about the stress analysis method, we're going to go into and talk about the LEM and carry out some of the modelling. So you can analyse a slope model by different analysis methods, and now I'm going to show you how to analyse a slope with the limit equilibrium method. So first of all, I'm just going to check off the mesh, the boundary conditions, and assign material properties to the surfaces. Just going to give it all just drag and drop these across straight from the works tree. We'll do the same for the nails. As you see, it always turns black when it's been created. So now I'm going to go up to the Limit Equilibrium Method ribbon tab and just select and define the arch surface. Just call it arch 1, and now we just create the grid and the tangents at the top. So here's the grid being created. We just draw where the arch begins and where we want it to end, and we can put the number as well that we want, the number of arches we want to have, and then just apply that. And we could have a multitude of these, so we're just going to create another one for a different case and do exactly the same thing, but put the grid in a different location. So we just put the passage point, and we can put the 2 points at the start and also at the end of the grid, so we just use the snap. So just creating the passing point, and there you go. Those are the two grids being selected there. So now I'm quickly going to turn these two layers off and go up to the Limit Equilibrium Method tab and create the polygonal failure surfaces. So I just want to input the information there. So we can select the first point and the end point, and we just use it like a spline all the way through. There you go, cutting through both surfaces, and the points come up as well. So that is our polygonal line has been created for our failure surface. So we can just going to go up to the check these off a second, and then just go up to the Limit Equilibrium method again and go for the arc passing limits. And all we can do here, we can limit the number of arcs for the analysis, and we can select where we place them. So we're going to select them on the toe and the top of the slope. We can also put values in, so I'll just demonstrate this now and then I'll change the values. Okay, so there we have the two effectively splices going down through. So now I'm just going to turn off the boundary conditions and just go up to the LEM tab again and create a line load. It's going to be a linear load. So just select the location where I want the load to be placed and put the number of kilonewtons. So I just want to put -10, -10. Obviously it's can change from end to end. Now it's going to create the analysis case for the LEM as well, so just going to activate the surfaces, add all the boundary conditions and add the loads. You can create multiple analysis cases in the same model file by choosing a different load and boundary conditions, and then I'm just going to carry out the optimize the design. So I've just added the water as well. So now I'm just going to go back into the presentation mode and we'll look at the analysis results after. So just going to look at the stress analysis method, or SAM. So the built-in stress analysis method, or SAM, in SolidWorks combines the accuracy of finite element analysis with fast runtime of the limit equilibrium method. You can get the output for ground deformation, stresses, the pore water through the finite element is considerably smaller analysis time, faster analysis time. Since stress is computed at each node in the model and then projected along the failure surface, it is recommended to use high order elements or elements with mid-sized nodes during the mesh generation. So just going to bring in the complete analysis model. So in this model we've carried out 3 different types of analysis. So the LEM, the SRM and also the SAM. So now I'm just going to go through some of the results. So just look through the stress reduction method and the factor of safety, which we've got there, which is automatically worked out. So we can just look at the effective stresses. You can also apply different loads and look at them in different directions from all the drop down menus. So I just want to look at the displacements and the total displacement. So you see here, there is the plane or the failure surface. So we can also look at the horizontal as well, and that's also looking at the failure plane, and we get a nice graphic, and also we get the legend. We can change some of the different colours with it and do some results tagging as well. So we can just select it at any given area, and we can also get it in a table format. So now I'm going to look at the extract results feature. So for the SRM, so we just look at the horizontal displacements and stress reduction. So we can just select a few points, and they're selected. We can look at them in a table format, and we'll get the results out. So now we look at the results. Just going to close this window. Now we're going to look at the on-curve diagram. So I've just selected it from the tab, and now the on-curve diagram is used to represent a results value for the on-curve. So I'm just going to select that. So the 2 points, as you can see, I've selected the surface, and you can see the values as well coming up. So we can select any edge and plot the profile. As you see, that's come out on there. So I just want to check off the diagrams. Now we're going to look at the forces in the structural elements, or in the nails themselves. So just look at the embedded trusses. As you see here are the forces, and we get the legend down the side as well. So I'm just going to switch to the pre-processing and turn off the mesh. Then we're just going to look at some of the LEM results. So that's the mesh was switched off. So just look at the arch failure surface. You can see that's the results coming out there. And you can see the factor of safety is being created. And you can select different points for different arches. So now we're going to look at the different factors of safety for the different failure surfaces in a different method. So the SRM, we can see it's got 1.6 factor of safety. Look here for the SEM as well, and you've got a factor of safety of 1.3. So as you can see, we've looked at the factor of safety of different modes. So this way you can analyse your slope with different analysis methods in the same model file. Then it will save time in the long run. So SoilWorks also generates a report automatically. This is a Word document, and it contains all of your different analysis types and drawings and tables. You see you've got the material properties and also their analysis results. So now I'm just going to go back into the presentation after showing you the report. So now just give you a summary of what we've just done in the modelling space. So we've had accuracy of the results in slope stability analysis, and it depends on the geometry in your modelling space, the material properties for the ground and also the structural elements, loads and the correct pore water pressure profile. The analysis can be performed by either limit equilibrium or finite element methods. The limit equilibrium method is easy to implement, has little analysis time, but the results output is limited. The finite element method gives results output for stresses, deformations, but requires setting up of mesh and longer runtime. So the stress analysis method, or SAM, combines accuracy and speed of the C-phi reduction and limit equilibrium analysis. So just going on to just quickly cover why SoilWorks, and then going back to another model. So SoilWorks offers an intuitive CAD-based drawing environment. You can build your slope model just from scratch and just import it straight from a CAD geometry. A slope can be analysed by 3 different ways, all in the same model, and thereby it optimises the design and speeds up your design process. The slope stability can also be coupled with consolidation and seepage effects. Now I'm going to switch over to the modelling space and take you to a new model. So this is the model of the embankment construction on soft soil. So just going to activate the PBT drains, which are installed to accelerate the consolidation in the clay layers. So we just selected those. And we just want to simulate the construction stages. So we've got the different embankments there. So we've got embankment 1, embankment 2 and embankment 3. And we're just going to look at the consolidation analysis, which is performed in the soft ground module of SoilWorks. So I've already analysed this model for consolidation in clay layers. So just going to go to the post-processing mode, look at some of the results. So it's going to show the results for the settlement with different stages. So you can see the settlement of different stages in this graphical form down at the bottom. Also got the settlement in a table format as well through the different stages. We can also look at the consolidation settlement and degree of consolidation graph by stages as well. So we can look at that in time intervals if we want to. So we can look at the increase in soil strength by stages. So the ground stress, the increase in strength, and also just look at the tons per metre squared. So as you can see the increase in the ground strength with the stages as you increase the volume of material on top. I'm just going to go over to 1D consolidation and going to export this model over into the slope model. So we've made this into a slope model, and now we want to bring across the actual slope module with it open inside. So as you see, we've opened the model in the slope stability function. So now we've got this open, we're going to create an arc surface. So let's name it arc 1, and this is the limit equilibrium method. So just create our matrix, and then we're just going to draw the arch. Okay, we just want to switch that up to 5, 6. Again, that's been created. Now we just want to carry out the analysis. Modify the construction stages quickly first. Everything's been highlighted in there. Drag and drop it all across. I'm just going to run the analysis very quickly, and just for the construction of the embankment. Now I'm going to show you the safety factor. You see that? So as we see, we can do exactly the same thing we did previously by picking different points and find the different factors of safety and the arc surface. So now that we've taken this model over into slope stability, it just gives you, this way we can couple the consolidation analysis with the slope stability for embankment construction on soft soils. And now I'm going to take you straight back into the presentation and close. So now we're just back in why soil works, and just we're going to discuss the last few points. So just talking about the robust mesh generation features to generate automatic mesh for any complicated geometry, which is a really neat feature within the program. Practical reinforcements such as nails, anchors, piles and geogrids and things of that nature can be considered, and you can select them from drop-down menus very quickly and efficiently. The parametric and coupled analysis features streamline your design process and increase efficiency. And also the dynamic report generation is in Word format and is inclusive of the analysis results tables and images, which make it very easy for you to move on with your design process. So now to just close, thank you everybody for attending the webinar today. I hope you've enjoyed it. Please do, by all means, this will be uploaded to YouTube, but subscribe to the YouTube channel. We are also on Facebook, LinkedIn, Twitter and all the other mediums. We're building up these as we go along. My name's been Adam Kane, and I've enjoyed taking you through this webinar today. If you do want a bespoke demonstration, please contact the UK support team and we'll be more than happy to help. The number's on the screen there, and we've also got the UK support email address if you've got any queries. We've had a couple of questions, but we're just going to leave it and we're going to answer those in an email form. So thank you for listening, and I look forward to doing the next webinar with you. Thank you.